and welcome to the notes about chemical equilibrium, sometimes also known as dynamic equilibrium. So there's some things that only happen one way. But others, most things, are reversible. When you eat, you don't get fatter and fatter and fatter and fatter. And even if you do get fat, there are ways to go backwards. So reversible means that the equation can happen the way it's written. Okay, the reaction can go from left to right, but it can also happen the other way, from right to left. Okay, and so I've just written it here. The forwards reaction is the way we normally see it. You can see this reaction is endothermic. The backwards reaction is just going backwards. So just rewrote it in our sort of normal left to right kind of writing. So here's it. The products react to make the reactants again. Reverse the potential energy diagram because now it's going the other way. And it's now an exothermic reaction when you go backwards. Pretty cool. We know reactions happen when particles collide, especially in gases or aqueous solutions. Solids and liquids are a little bit more complicated, especially solids, and those reactions tend to take a lot longer, like millions of years. So we're going to think about gases and aqueous solutions only. You need to have enough energy to go when the reactants collide, make a product. Same thing doesn't stop happening just because you've made the products. The products now can collide with each other and make a reactant. We know that it's not like every time two things collide, they react. Sometimes they collide and bounce back and nothing happened. It depends on the orientation and the speed of the particles. And when we look at the potential energy diagrams of these two reactions, you can start to imagine that the activation energy is not the same, that the shapes of the molecules are not the same, and so that they're not going to have the same probability of happening. So maybe with one of the collisions, if it collides 4 times, the 4th time, reaction. And maybe with the other one, it has to collide 10 times before it reacts, or 2 times. They're not going to be the same. Let's try an experiment. I used beakers for this because it's really easy to measure. It doesn't matter how much water you add, so just try it. We've got 2 rules. First, in rule 1, if you have any water in the cup, you got to pour half of it into cup 2. I have no water in the cup. Second, in cup 2, if you have water in the cup, you have to pour 1/3 of it into cup 1. Got 150 milliliters, I'm going to pour 50 milliliters. All right, here's our cups now. Got 50 mils here, half of that is 25. 100 mils here, 1/3 of that is 33. Let's go. Pour. Pour. Okay, now our volumes have changed again. Half of this, 1/3 of this. Pour. Pour. Okay, next up. Now we have 60 and 90. Half of that, 1/3 of that. Did you just notice something? Because it looks to me like we just poured 30 mils and 30 mils. So our volumes didn't change. Huh. Try it again. Still the same amount back and forth. Our volumes didn't change. What do you think? What if we started with a different amount of water? We could try it. Or if we had different rules, instead of pouring a half of it, we could pour a quarter of it only. And I'm going to tell you that these first two things don't affect the end result. Weird, but true. The last thing, different rules, would affect the end result. So here it shows we started with 150 mils. We started with 0 mils. First, we got less and less water in cup 2, more and more in cup 1, but they evened out. 90 in cup 1, 60 in cup 2. We started with a different amount. Same result. Crazy. Okay, so let's think about chemical reactions. At the beginning, lots of reactants and few products, or maybe none. You can only go forward. There aren't really products to collide with each other. So reactants collide, bam, reaction, we start making products. Well, now, we've got a bunch of products in here and some reactants. So there's less reactants to collide with each other. So that rate goes down. Look over here. First, concentration was decreasing really fast because it was turning into products really fast. Lots of collisions, lots of reactions. But less and less and less. It's changing less and less fast. Okay, but now the products, there's enough of them, they start to collide, bam, and make reactants again. And so the amount of products that we have, first it increases really fast because that's all we're making, but then those products start having collisions, and they don't go down, but they just don't go up really fast again, and bam, we end up in this equilibrium state where our concentrations stop changing. So there's two definitions you need to know for equilibrium. Concentration of the reactants and products will stop changing. It doesn't mean that they're equal. There might be more of one thing than the other thing. That's normal. But whatever the concentration of reactants is, if you measure it 5 minutes later, 30 seconds later, whatever, it's going to be the same. Same with the products. Whatever the concentration of products is, it stops changing. And the rate of the forward reaction and the reverse reaction, forward and reverse, is going to be the same. Because if you had a higher rate for one of the reactions, you would start making more of the opposite thing, and that concentration would change. So you have to be evenly going back and forth and back and forth. Again, it doesn't matter where you start. At first, it's really weird, but then you get to equilibrium. There are 5 common mistakes that students make. Number 1, they think that at equilibrium, the concentration of products and reactants are equal. Equilibrium. Not quite. The equal part is about the rates. Okay? The forward reaction and the backwards reaction must happen at the same rate. But the equal part is not about the concentrations. Number 2, you think the reactions stop. We're done. The concentrations aren't changing. They're not changing, but the reactions are still happening. It's just that there are gajillions of particles. And so they're all reacting, but the rates are the same. Number 3, we think the pH is neutral. Makes sense, equilibrium, balance. Not true. Okay, because you could have equilibrium with one of the products that's now at equilibrium. It's now staying the same. being an H plus ion, which would make your mixture acidic, or an OH ion, which would make it basic. So it could be acidic, it could be basic, it could be neutral. It just means that nothing is changing. It's not becoming more acidic or less acidic over time. Students like to think, well, we're going back and forth. We're going from reactant to product, product to reactant, back and forth and back and forth. And if you look at the individual tiny molecules, yes, that's what's happening. They're colliding with each other, bam, making new stuff, colliding again, bam, going back to the originals. But at the bigger level, at the level we can measure, the changes do not happen. Concentrations stay the same. And last, students think that the ratio at equilibrium, talked about this already, depends on how much you start on. And it doesn't. It depends on the reaction and how likely each collision is. So don't make those mistakes. So back to that last one, the ratio at equilibrium depends on how much we started with. Let's look at this and look at different reactions that have different ratios. So in reaction 1, okay, so we've got questions about this. Reaction 1, we have 2 products and 2 of each reactant. In reaction 2, we have 1, 2, 3 products, 1 of each reactant. And in reaction 3, we have 1 product and 1, 2, 3 of each reactant. So we can talk about how that mixture is with something called K. K is the equilibrium constant. It's a big K, capital K, don't write a small k. And K is the ratio of products divided by reactants. It's called the constant because the ratio is going to be the same for the same reaction, the same temperature. It doesn't matter how much you started with, it's measuring the ratio at equilibrium, once things have stopped changing, once the reaction rates are equal, and once the concentration of reactants and products stay exactly the same. So if we went back to our cup of water experiment for a second and tried it with a little bit of water, we could see that the ratio, not at the beginning, but at equilibrium, is 0.7. We tried it with more water, 500 milliliters total of water. Still, the ratio at equilibrium is 0.7. So quickly, let's look at this in real reactions. The K is the ratio of products to reaction for one particular reaction. And if it's really big, it means you have mostly products. Products divided by reactants is greater than like 1,000. If it's in the middle, somewhere near 1, that's about the same, products and reactants. And if it's very, very small, it means you have a lot of reactants left, you didn't make a lot of products. So lastly, let's go back and look at the carbon reactions in the ocean. And the key thing is they are reversible. Who would have thought? Pretty cool. Okay, so first reaction. Carbon dioxide combines with water to make carbonic acid. Reversible. Second reaction. Carbonic acid loses an H plus ion. It's a weak acid and releases that H plus ion. And last reaction is talking about calcium carbonate, what shells are made of. Calcium carbonate almost never dissolves in pure water. But if we add those H plus ions in it, bam, sometimes it is more likely to dissolve and make the calcium ions the bicarbonate ion, and those shells just kind of fall apart. All right, so that is it for today's notes. If you are thinking of taking AP, continue with part